Welcome back to the Fractional Calculus seminar series. Today we have Professor Gopalakrishnan, who received his BS degree from Bangalore University, Master's degree in Engineering Mechanics from IIT Madras, Chennai, and PhD degree from School of Aeronautics and Astronautics from Purdue University, USA in the year December 1992. After his PhD, he was a postdoctoral fellow in the Department of Mechanical Engineering at Georgia Institute of Technology. In the year November 1997, he joined the Department of Aerospace Engineering at Indian Institute of Science, Bangalore, where currently he is a senior professor. His main research interests are wave propagation in complex media, computational material science, computational mechanics, smart structures, structural health monitoring, MEMS, and nanocomposite structures. Professor Gopalakrishnan has extensively published his work on many top international journals. He has a total of 245 international journal papers, 9 graduate level textbooks, 2 undergraduate books, 15 book chapters, and 180 international conference papers. He has an H index of 56 in Google Scholar with nearly 12,000 citations, which is the highest in India for any researcher in aerospace domain. He is the editorial board of 5 international journals and editor-in-chief of ISSS, a journal of micro and smart systems, and associate editor of smart materials and structural health monitoring international journals. Professor Gopalakrishnan is decorated with many awards and honors, which include International Structural Health Monitoring Person of the Year Awards 2016, instituted by the Sage Publications, Fellow of the Indian National Academy of Engineering, Fellow of the Indian Academy of Sciences, Associate Fellow of AIAA, Distinguished Alumnus Award, Indian Institute of Technology Madras, Satish Dhawan Young Scientist Award by the Government of Karnataka, Biren Roy Trust Award of Aeronautical Society of India, Alumni Award of Excellence in Research at IAC in the year 2013, Royal Academy of Engineering UK Distinguished Visiting Fellowship. He was elected Fellow of the Institute of Mechanical Engineers UK in the year 2020. Professor Gopalakrishnan figures in Stanford list are at top 2% of scientists in the world for 4 consecutive years. This year, he will receive the ASAME Founders Medal for his outstanding contributions for structural health monitoring and NDE. He has guided 32 PhDs, 7 MTech research, for 23 MTech students, and has attracted funding of over $5 million in research fundings. We are very happy to have you here. You may please begin the talk.
Thank you. Thank you very much. Sorry for the delay because of the technology problem. Uh, thanks for the kind introduction. So today I will be talking about the spectral analysis for wave propagation in non-local waveguides. So we'll come to that, what are non-local, as we go along. Next slide, please. Can I have the next slide?
Yes, I'm trying to change 1 minute.
Okay. So this work is based on the PhD thesis of my two former students, Venkat and Narendra. Next. So my talk outline is for those who doesn't know wave propagation, I'll just basically introduce very briefly wave propagation and spectral analysis. Then we will define what are local models and what are non-local models, and how do you determine the wave modes, and what are the non-physical, unphysical phenomenon that you see in this, and whether that exists or not. And to answer that, we use two kinds of relation, the concept of causality, and we bring in Karmer-Kronig relations and also Einstein causality. Then we'll present some wave modes in some non-local waveguides and show how a non-physical phenomenon occurs and how do you answer this using these causality relations. And we'll also see some key observation and then conclude. Next slide, please. So waves in engineering is found all over. You would have, so basically you will have the longitudinal waves, basically in rods, in structures. Beams are similar to rod, but they support transverse motion. So you see the pattern how the wave propagates there. Then you have water waves, which is well known. And in case when there is a earthquake, you have surface waves, what are called Rayleigh wave, P wave, S wave, etc. Next slide, please. And there are different forms of waves, especially in structures. One is called the bulk wave, and where some waves, as they propagate, they retain the shape, whereas in others, as you propagate, it changes the shape. These are called dispersive and non-dispersive. But in case of a 2D medium, you have what are called guided waves. It is basically on a thin plate, very thin plate, where when there is an incident pulse, and there are two kinds of modes, what are called symmetric and antisymmetric modes. Next, please. Can you go to the next slide?
Yeah, I'm trying one more.
Okay, next. Go to the next. Yeah. So some terminologies you should know. Any structure that transmits wave is called a waveguide, and it transmits the wave in particular direction. For example, in rod, it goes along the axis of the rod. In beam, it goes in the transverse to the axis of the rod. So these are called longitudinal waveguide or the bending waveguide. So in membrane waveguide, plate wave, shell, etc. And every wave is characterized by a number called wave number. And the wave number determines what is the type of the wave. If the wave number, it's always a function of frequency. If it is a linear function of frequency, then the waves are called non-dispersive and the signal does not change as it propagates. If the wave number is a complex function of frequency, then the waves are called dispersive and the signal changes its shape as it propagates. Next slide, please. Then we bring in the concept of speed. What is the speed of the wave? There are two kinds of speed. One is the speed of the particle, individual particle. That is what is called phase speed, where the phase speed is given by the a particular frequency divided by the wave number. And the other concept is when the group of particle bind together and then propagate. And these are called the group speeds. And it is given by the differential of d omega by dt. And the speeds of the group speed when you do an experiment basically and measure the response and find the speed, what's the speed you get is the group speed. That has more meaning. When the group speed is not a function of frequency, then the wave will be non-dispersive, which will retain its shape. When the group speed is a function of frequency, it changes its shape. And where you will have higher frequency will travel faster, lower frequency will travel slower. So you get a very combination of all kinds of waves. And the wavelength is basically 1 over k or 2 pi by k. And that's very important when you actually do a numerical modeling of the waves, especially in case like finite elements. Next, please. So let's take a simple second order system, a partial differential equation. Here, A, B, C are essentially the constants. So what we do in spectral analysis is we now transform this into frequency domain using discrete Fourier transform. The numerical implementation of the discrete Fourier transform is the fast Fourier transform. So when you apply this discrete Fourier transform, it converts a partial differential equation into a sum of ordinary differential equation, and which is of constant coefficient type. So you know the solution is exponential. When you substitute this exponential, you get a characteristic equation for the wave number, which we use to solve. this particular wave number will tell what is the type of wave. So if you look at the wave number K12 here, it has both the first part and the second part. And the second part is called the radical. And the behavior is, if you look at it, it completely depends upon the behavior of the radical. That is, you will have b squared by 4a squared greater than c omega squared by a, less than c omega squared by a, or equal to a. And suppose we say if b is 0, then you will have the first wave number is a linear function of frequency. It is non-dispersive, similar to the rod. Uh, Now let us take the three cases. Next slide, please. So if b square equal to, that is the radical becomes 0, the wave number is purely imaginary. So when the wave number is real, it propagates. If it is purely imaginary, it damps out. And when if you take the definition of the phase speed and group speed, these are complex function of frequency, and hence it will be basic for the case 2, it will be dispersive. And now if you look at the radical, in order that the imaginary becomes real, we call it as the transition frequency, and that basically is given by b by 2 root AC. What it means is, by just manipulating ABC, you can change the type of the wave going into a waveguide. So that is the advantage of the spectral analysis that we have shown. Next slide, please. Similarly, we can do for a fourth order system. So fourth order system, we take a fourth order system which is given on the top left hand corner. And if you use a Fourier transform and convert it, you will get a characteristic equation for the wave number, which is given here. And again, it depends upon what is the value of c omega n square minus b, if it is greater or lesser. And for example, if it is greater, then you will get two real modes and two complex modes. The complex mode basically will not propagate. It is called evanescent mode. However, if c omega n square is less than b, that means the k is complex. So what does the complex k mean? As the wave propagates, it also attenuates. So that adds damping to the system. So you will completely understand what is the type of waves based on the simple analysis using Fourier transform. Next slide, please. So now let us come to local and non-local models. So normally we use all these continuum theories are called classical continuum, which is given on the left-hand side. Then there is a non-local continuum, and there is a discretized continuum. So what is the difference between all of this? In the classical continuum, we say that the material, if you take a material property at the one point, it's also same at all other points. Whereas in the non-local continuum, we say that the material point x is influenced by all the point within, you take another point x bar, or if you draw a circle in that, there are multiple points there. So the material points is dependent upon not only of that point, on all the points surrounding it. A discretized version of this non-local model is what we call the peridynamics model. And the problem here is, when you are doing analysis at the atomistic level, the continuum model which we normally use, where we use Hooke's law, basically stress is equal to some modulus times strain, does not is very convenient at the atomistic level, because it doesn't capture the wave dispersion at that level, and you have unrealistic predictions and damage, and the microstructure of the solid is not taken into account. So we need to go to the non-local models. Next slide, please. So here I have given the local model. As I said, the stress or a force at a point influences the strain or displacement only at that point. For example, we have the Hooke's law, sigma equal to E epsilon. In the non-local model, the stress and force at a point influences not only at that point, but all the points surrounding it. So we put a circle, which is, we call it as horizon. For example, there are many local theories. I will come to that. What there is very famous, what is called Ehringen or non-local theory, where the stress and strain are given in terms of a integral function, where this alpha is a kernel function, sigma non-local is equal to E times this integral. Whereas if you take the peridynamic, which is given below, which is slightly different. So non-local formulations are essentially when you use an integral, in order to convert it into a solvable thing, we introduce what are called length scale parameters. So length scale parameter becomes a part of the solution process. Next slide, please. So if you look at it, there are different kinds of non-local formulation. One is the integral type non-local formulation and the gradient type non-local formulation. So in the gradient type, what we do is we take any displacement or any field and we perturb by some distance xi and expand it in Taylor series. And we get something which is below f of xt, which will be a sum, where this I of m is the length scale parameter comes into picture, which is a function of the material parameters or sectional properties, etc. For example, if you take Ehringen's theory, this model will convert it into what is given below here. Essentially, what it says is the here L1, L2, etc. are the length scale parameters. So essentially, this integral is transformed into a governing differential equation by series of mathematical modulation. So sigma is not equal to E times epsilon. Sigma is equal to something else where the length scale parameter comes into picture. Next thing, please. So if you look at Ehringen models or peridynamic model, they are called phenomenological model as these are continuum models with the length scale parameter built into it. So essentially, uh, there also exist a physically based non-local models where they use a different procedure to derive the equation of motion that also builds in the length scale parameters. So if you look at the equations given here, the L1, L2, L3 are all the length scale parameter giving there. So essentially, how does the wave propagate here? What are the properties that you get? Whether there are, it will make sense at the atomistic level, what we are looking at. Next, please. So the problem here is how do we identify the length scale parameters? Some of them have done many experiments to get it, but many times we have to use some other theory to actually get it. So in this presentation, I'm just going to demonstrate this non-local theory wave modes only in a 1D setup where the motion can be either axially or transversely. Axial motion is called a rod, transverse motion is called beam. They get a regular rod and the elementary beam is the Bernoulli-Euler beam. Sometimes we use higher order beam theories. So that is, and we will look at all the wave modes and we will see whether there are unphysical or non-causal features that are going to be here. And if so, we'll try to explain with certain causality theorem that we'll bring in and see whether how this can be modified. Next, please. So before going that, we need to understand because we are looking at the atomistic level, the most of the atomistic models are lattice dynamics models. And the lattice dynamics model is essentially a spring mass, sometimes damper models. Here I have not considered damper. A typical lattice dynamics of a solid will have atoms of mass m connected by series of springs, and the springs can be neighbor. If there are two atoms which are very close, there will be neighbor interaction, but these atoms can also interact with the farther, which are called the long range interaction. If we write the governing differential of equation of motion, we can do that. It is just like mx double dot equal to k times x, where you get this equation in terms of the uh, spring constant. And we do a Fourier transform of that, and we get the wave number relation, which is given below it, below 2. So if you look at this here, the whole idea is how does the non-local theory compare with the lattice dynamics approximation? How do we use this to identify the scale parameters? And what is the origin of the negative speed and how we can actually explain it? Next, please. So here I have given three different non-local models. One is called the strain gradient model, and the equation of motion for a simple rod is given by the first equation. And if you take a Fourier transform, on the right of it is the frequency wave number equation. Second is the strain gradient rod or Arran rod, and the right side is the wave number equation. And the third is the bond-based peridynamics equation. And against right is the frequency equation. If we plot the wave numbers and also the group speeds and the phase speed, these are given in the first three figures. And the bottom, I have plotted the same for the lattice dynamics. If you look at it, the wave number difference is completely different. One thing is very clear is that in this one, we have shown the whole idea of showing is where are the unphysical phenomenon is coming. So only we are using only the real part of decay, that is propagating part. And if you look at it, the black one is the peridynamics model, and the peridynamics model show the effect of negative speeds. What does negative speed means? When you actually have a input to the structure, the wave will propagate in the direction. That is what normally. When it propagates in the negative direction, then the idea of the mass conservation and momentum conservation is broken there. So how do we explain that? And if you look at it, the peridynamics model and also the lattice model agree very well. Their results agree very well. Whereas if you take the arrangements and strain gradient, they differ quite a bit, except at low frequencies. Next, please. So Erringen used the lattice dynamics model to actually get the value of the scale parameters as 0.39 by actually looking at the waves at the end of the first Baloin zone. And now that we have the lattice dynamic model, and we have all these three models. Using these three, we can actually estimate the value of the scaling parameter E naught A, for example, by comparing the dispersion or the speeds or the wave number between these three models. For example, if you look at the strain gradient model, the value of the scale parameter is 2 delta, where delta is the horizon of the peridynamic model. Similarly, in the stress gradient model, we can get that. So this is basically by comparing these results, because that is a problem if we want to match all the three atomistic model to the lattice dynamic model. And we can also get the lattice dynamic spacing in terms of peridynamics model, which is the third equation which is given. And this is actually more exact. In contrast, in normal, popularly people use horizon by the n. N is the number of terms in the series in the peridynamics model, which I showed before. Next, please. So if you look at it, you will see that in the lattice dynamic, if you take one interaction, two interaction, three interaction, up to five interaction, you can see that more number of interaction, the long range, the slope of the wave number keeps on changing, indicating that these are the regions of the negative speeds or zero speeds, which should not be allowed. So what is the reason? So if you look at some of the literature, the author said the negative speeds can occur if there is a length scale within a length scale. That means if you look at the Peridynamics and the Arran models, they show the existence of scale within a scale. And that is the reason why you could see negative speeds in these models. So hence the negative speed and multiple K having, because lattice models, more number of masses, more number of modes you get, multiple K are consequence of the fundamental assumption in an integral type non-locality. So that is because of the long range interaction. Next, please. So now let us look at some of the wave methods, wave modes in different waveguides. I've taken a few examples here to show that. Next. So this is a simple strain gradient model. So in the strain gradient model, there is the first equation is the constitutive model, where sigma, that is stress, is equal to strain minus L square uh, is the scale parameter, and there is a second order derivative in strain, and there is a minus sign between epsilon and the second term. And there is always, this sign of this is always called the paradox in the non-local theory. People say that, and this still an open area. When you do a Taylor series expansion of the stress, you will get a positive sign, but here I have taken negative sign. I have also shown in the next slide, I'll show how the positive and negative completely changes the wave behavior. So here to use this, we use a spectral analysis, we get the wave number. If you look at it, the first mode is completely real, it is propagating. And the second mode is completely damping, that is imaginary. And the speeds, the group speed is very good at low frequency, but goes to an exorbitantly high unbounded speed. Again, this is unphysical. You cannot have a waveguide having 13,000 meters per second as a speed, which is very, very high. So this is one of the problems of this, and this is how the wave, and this is unphysical here. Next, please. If you take the same rod, if you take a positive sign, this is what the actual thing is, then you see something weird happening. The third equation is the wave equation. That means k to the power of 4 means there are four roots to the equation. You'll get four modes. Two are normally forward propagating and two are backward propagating. We will only consider first two modes. If you look at it, both are complex, and you will see that the wave number initially starts high, dips, and again goes there. The dipping part here is the problem of instability, mainly because there'll be a change in speed and the speed may become negative. And same thing happens both. So this is a completely unstable model. Next, please. So if you look at it, the first mode, you will see it starts at an infinite negative speed and goes to a finite one, which is unphysical. The second one starts decently, goes to negative, and again goes back. So these are not allowed. These cannot happen. So this model is a highly unstable model, and we have proved this using doing spectral analysis. Next, please. So now we take next is the origin theory, and the equation of motion is given by here. So you will see this is a unique equation which has a partial derivative in time, space, and you will have an equation which is a mixed derivative, which is a function of both x and t. And if you do a frequency analysis, you will get a wave number which has a numerator and denominator. And there is a chances that the denominator can go to zero. That means the wave number will go to infinity, and the frequency at which it happens is called the escape frequency. And at the escape frequency, what happens is the wave completely, the group speed becomes zero, and the wave completely stops propagating. So the real and imaginary part we have shown here, and the only one real part, the speed we have shown that after some frequency, escape frequency, the wave does not propagate here. Next, please. So now we use, that's the second order, we'll use a fourth order theory. Fourth order theory, you will have much more complicated equation. And if you look at it, you will have the equation which is fourth order. That means it will have four modes, two forward and two backward. So if you take the first two modes, one is purely real, one is purely imaginary. Again, the behavior is same as the real mode, will have the same escape frequency as well as what is happening to the this one. It doesn't go to zero, but it comes to a smaller value compared to the second order theory. And these are well behaved models. Next. So the other one is the more general lattice model. This is a non-standard model derived from the lattice model, which has many length scale parameters. And this is actually very commonly used for the people who do the atomistic wave propagation. And the frequency spectrum is given here. If you look at it, very nice and interesting thing. First mode is completely real. The red one is imaginary here. So if you look at it, it's completely zero. The imaginary is zero. The real part, it goes. And the second mode is it starts imaginary and after some time becomes real. That means there is a cutoff frequency at which the evanescent mode will become propagating mode. So this is something very unique, something which is very similar what we see in some of the classical beam models. Next, please. So the speed here is again very similar to the Erringen rod, but you see the second one, because it's imaginary to start with, there is nothing, no propagation until cutoff frequency, and then it starts propagating. Next, please. So now let us look at some of the beam type models. Again, we consider strain gradient with positive sign, negative sign, Erringen model. And we'll see that if you look at it, now the beam supports the transverse motion. So you will have a system which is sixth order in space, if you look at it. So there will be six modes, three propagating and three evanescent. So if you look at that, all the three is propagated, is plotted in the left side, and the individual modes are propagated in the right side. If you look at it, one mode is purely real and other modes are complex. And you will see that the red one, which is imaginary, there is a coalescence of mode in the imaginary. And whenever you have a coalescence of mode, then it also says it's unstable. You will have a problem because for the same frequency, you will have multiple wave numbers, which is not possible. Next. So if you look at it, these are the speeds. And again, you have the third mode, which has a negative speed, and you have unrealistic high speed, all kinds of unphysical phenomenon you can see in the strain gradient, in this strain gradient rod. And you will also see the coalescence is there in the imaginary part. And sometimes you will also, as we'll see in the next few models, you'll also have coalescence in the real part. So basically, we need to explain why this unphysical happening here. Next. So this is the beam with positive sign, the strain gradient model. Again, you see the pattern is similar. Only thing is the real and imaginary part are getting interchanged. All the modes are complex, and you will see coalescence instead of imaginary, you see coalescence is happening in the real mode. And next slide, please. And you will see that it starts with negative infinity and goes to a very high mode, the mode 1, and the mode 2 again goes to infinity. So completely unphysical, unstable model that you have in this case for the case of beam when you use strain gradient models. Next, please. Then you will use the same like a strain gradient with negative sign, but we also add an inertial term. And what happens here is it kind of stabilizes the instability in those models. And if you look at the wave number group speed plot here, again, you see on the left side, all the three plots are there. And the first mode is completely real. Second mode is wave number becomes zero. That means the speed becomes infinite. Again, it is kind of unreasonable to have. And the third mode, again, is not stable. Next, please. So if you look at it, the same thing. You have the group speed and wave speed here. And the speed starts at very high and goes to zero. Very high, unphysical, but the mode one is well behaved. So you can see that different models exhibit different kinds of wave modes. These are some of them cannot happen because they are unphysical, because of very high speeds and negative speeds or sometimes zero speeds. Next, please. So this is another model, which is the Arran model. And if you see that Arran model is very well behaved, you have a one real mode, one imaginary mode, and you have a nicely the speed plots, which starts at a finite speed and goes to a reasonably high and comes back. So it is more stable model compared to the strain gradient model. Next, please. So what we have seen here is the non-local gradient model show frequency spectrum to be a polynomial equation in K. Hence, the number of roots of K or wave modes are finite in number, which is equal to the order of the polynomial or order of the spatial gradient. The combined strain and inertia gradient keeps the speed in bounded in some cases. Keeping the order of the inertia gradient equal to strain gradient introduces what are called the cutoff frequency. And the cutoff frequency ensures the physical realization of the wave behavior. The wave dispersion and wave dissipation either happens within a wave mode or in different wave modes. And some of the modes give unbounded speeds, some give zero speeds, some give negative speeds. So we need to explain all of this in the next few slides. Next, please. So before going to explanation, let's go to the integral model. So in the integral models, the governing equation is the first equation, and this model is called Zingel's model. So you have the basic hyperbolic rod equation to which you add an integral term, basically coming from the what are called the peridynamic component. And the frequency spectrum relation is given next. And here the basically the function G is given, and delta is a horizon. Horizon is you draw a circle close to your point, and that point, the material properties of that depends on not only on that point, on the points surrounding it. So the E is the material property. So actual material constant of these integral model is 3E by delta Q. And delta is as small if you take the atomistic level. And the left side figure is essentially the wave modes of the real and imaginary part. The red color is the imaginary part. And you see separately first wave mode. One thing we need to see, because of the integral nature, the integral is replaced by a summation. There are infinite modes. There are infinite modes. And we'll come to that. This is a problem with the integral model. How many? So to solve these infinite modes, we need to have infinite boundary condition. Is it physically possible? We don't have. For example, we have rod only, we have displacement and forces. We don't have infinite boundary conditions. So how do we answer that? So that's what we will see in the next few slides. Next, please. So this is the speeds. Again, the one of the modes goes to negative speeds, and then goes to a unbounded speed. Only one mode is well behaved. Next, please. So this is the same with the beta portion is taken out. This is called the Silling model. Silling is the one who brought in the bond-based peridynamics into it. And frequency equation is very similar to the lattice dynamics equation. And you have multiple modes, and multiple modes are having all kinds of behavior here. And if you isolate this, you will see the behavior here. Uh, uh, Unphysical, mainly because the wave number should not abruptly change the slope, and that means there is instability. And all the modes I see, this is happening. Next, please. And if you look at the wave speeds, you will see one is well behaved, and afterwards it goes to a negative point and goes back again. And some very interesting phenomenon is happening. So again, it exhibits unrealistic speed as well as negative speeds in these models, the integral models. And we have only plotted four modes here. Many modes, as you go higher and higher, the behavior is more interesting and complex. Next, please. So basically, we will see that these two models, there are infinite number of modes, and depending upon the constitutive model, the kernel function, there is no coalescence in these modes. And if you introduce a linear combination of the local and non-local constitutive model, we will see there are no coalescence of the mode, and there is no explicit negative speed. Very small region you find that. So in both these models, infinite group speeds are seen at lower omega. And uh, how do we solve this? So essentially, we have a solution which is a combination of uh, the two forward moving and the backward moving wave. The first equation minus iknx is k is the wave number, is the forward moving, and the next is the backward moving. And here the coefficients have to be determined based on the boundary conditions. Because n is infinity, we don't have infinite boundary conditions. So that is the major problem. And there also, the question that needs to be answered is, can infinite number of waves propagate in a given structure, which basically violates the mass and momentum conservation. So what does the infinite number of conditions mean? So we don't know these answers. So we need to find that. There exist reports on equivalence between integral type and non-local type gradient. And in wave dispersion terminology, it implies that there exists equivalence. And the number of wave modes in a model is directly related to the order of the spatial gradient. So in the simple rod, you will have second order in space, second order in time. So you have two boundary conditions in time and two boundary conditions in space. But in the peridynamic model, we have infinite. So where do we get infinite gradients and what does it mean? So these are some of the things that we will look at it in the next few slides. Next, please. So can we explain this unphysical phenomenon in non-local waveguides? So we bring in the principle of causality. What is causality? Here, the causality means the cause will always precedes the effect. This is a simple principle. So in wave literature, there are two different types of causality. One is called the Einstein causality. Another is called the primitive causality or the Karmer-Kronig relation. I've given you two papers which deal with it in more details, and people interested can see this. Next, please. So in the primitive or the Kramer-Kronig, it says that if the wave is complex, the real part and imaginary part are tied together and they are not independent each other. So I have given you two relations. You can go through those papers to get that. And if you feed the real part of the function, you can get the imaginary. And if you feed the imaginary, it gives you the real. And if they are matching very well, from either my governing equation or from this equation, then you say that the models are causal and you will not have any of these unphysical phenomena. And there are various versions. For the first version, G is what we call the system transfer function. We use that. And if you want to find the wave number, we will use the second equation, which can be derived from the first. And these essentials say that if the waves are dispersive, it is also dissipative or evanescent in a causal medium. Next, please. So upon closer examination, uh, the K form can be used for those models that shows only one wave mode, but we have multiple wave modes. So that may, whatever we get from there may not be useful. But we will use the solution and the wave number to construct the system transfer function G, which is a combination of the multi-wave system, and that will give whether the system is stable or not. So we will use both of these and show how we can actually use it. Next, please. So let us take a simple KK relation for a classical rod. So a rod is well behaved. You have a non-dispersive system. So here the imaginary part is 0. So when we feed the value in the K form for the in the KK relation, we do get imaginary 0. And that's what is shown here. But we will also consider, and we will use the second function here as the solution for A and B using the boundary condition and construct the system transfer function. When you plot the system transfer function, which is for multimode, we also see that there is a good relation there between the imaginary part obtained from KK relation and the imaginary part, which is 0 in the case of the rod. Next, please. The same thing we can see in the beam. Beam is a fourth order system, and the one mode is completely real, another mode is completely complex. So if you feed the real part and construct the imaginary part, we can exactly get that. So that means KK relation is valid because yeah, regular rod and beam are stable systems. Next, please. So let's take for the case of the origin rod, the stress gradient rod. And we apply this K form of the KK relation. And if you, and this is the original obtained from the equation of motion, which I presented before. Now I take the real part and I feed it to the KK. I get the exactly the same as the imaginary part, saying that the second order stress gradient theory is a stable theory, and we can use the same model to use it, the wave number obtained from the equation of motion to use it. Next, please. Now, how do we construct the G form, that is system transfer function? So I have taken a totally different model, inertial model. This is the last beam model, the rod model, which I had presented earlier. I use the Fourier transform, convert it into frequency domain, and the equation is a constant coefficient type. It will have 6 equations. I have left out all the, I'm considering an infinite bar. So I'm taking only the solution for the first 3 modes, which is given there, and I apply the boundary conditions. The force for the u du by dx and d square u by dx square at x equal to 0. And then next, please. From this, we can actually get the system transfer function. So G will be of this form, and we can get the system transfer function. If it, and this will again be complex, and it contains all the 3 modes because it is a multimodal phenomena. And the typically KK relation is not good when it is only multimodal if you use the K form. So we'll use the G form of the KK relation and find out, feed the real part and get the imaginary part. Next, please. So if you look at this, this is the G form. And when I feed the real part and get the imaginary part exactly coincides with what I get from the equation of motion. So that means this form is a stable form. So it doesn't have negative speeds, it doesn't go to unrealistic speeds, and it behaves very well. Next, please. So now let us take the strain gradient rod. Strain gradient rod was completely unstable with a positive sign. So if you use the KK relation, the imaginary part, what is given in the equation of motion is in the top, and what I get in KK is in the bottom. And this is more stable, and it gives me finite speed. And when I use this to construct my wave motion, it is propagating properly. So essentially, it alters. So I will take the wave number I got from KK relation and put it in my equation to do the wave propagation studies. So KK relation in that way is very useful. And we again applied this for the fourth order, the fourth order strain gradient model. And it is a very stable because whatever we fed in the real part and get the imaginary part, we compared it with the equation of motion solution, it matches very well. Next, please. So this is again the integral theories, the same problem. So I'm going through fast mainly because there are a lot of things to cover. So even here, those modes which were contributing to the negative speeds, it alters the wave number so that you will always get positive speeds in most of the cases. So that is the advantage of the KK relation. That's what I have showed here. Next, please. Next, we come to Einstein causality. So there exists another causality, which is Einstein causality. Here, the following condition has to be satisfied. The wave motion in the following sets is not allowed, that is infinite speeds, infinitesimally small speeds, instantaneous diffusion, and negative speeds. And these are completely needs to be avoided. So we remove those modes while calculating the wave motion. So these aspects have been, there are lots of papers in this area. And further, it is postulated that ancient causality sense, causality is not violated if that happens because we remove those modes. So this is something we can actually follow it. But more theoretical explanation of altering the wave numbers comes from the KK relation. Next, please. So now let's look at the wave motion in a peridynamic rod. So now we assume the Fourier transform, discrete Fourier transform, where the u hat is the wave coefficient, which has where we have to take infinite number of modes, where p is infinity. And we don't have that many number of boundary conditions. And the number of boundary condition is determined by the order of the wave number. In case of peridynamics, order of the wave number is infinity. But we don't have that many number of boundary conditions. So how do we handle it? And we have seen, except for one mode, all other modes based on Einstein causality can be removed. Can we say that only it is a second order gradient? And that's what we need to look at it. So let's see what we get it. Next. So here, this is the original equation I presented. And we convert the integral into summation. So n becomes infinity. And so that means infinity. So now we will say when n equal to 1, n equal to 2, n equal to 3, what are the different forms of the equation we get? When n equal to 1 in this equation, you will get this, and this is the weak form of the equation, which gives me the boundary condition, which is simple rod. And when n equal to 2, so where L1 is 1 in this case. But if you take L equal to 2, I'll get 2 length scale parameter and the boundary condition is there. N is equal to 3, I get 3 boundary conditions, and the governing differential equation is also becoming higher and higher. And when N equal to 4, 5, 6, it becomes more complex. Next, please. So now the question is for the n numbers you take, you will have the first variable v, dv by dx, first gradient, second gradient, third gradient, fourth gradient. It goes on and on and on. So higher n implies means more number of boundary conditions are required, but we don't have that. And as the n tends to infinity, this summation will become like this. This can be shown by as an integral, and you will have the gradients can be found from here. However, in the case of rod, the only available boundary condition is the kind of impact that is the Neumann boundary condition or the natural boundary condition, and one on the Dirichlet boundary condition or the displacement boundary condition. I have only two for a rod. So how do we fix n here when you have infinite modes? Next, please. So what we have done here is, let's take only one mode. So this is the force and this is the deformation. When you take mode n equal to 2, the governing equation is here and these are the boundary conditions. So the above choice of the boundary condition is motivated by the consistency between the number of modes, number of conditions and the spatial gradient order. So here if you take the second mode, the spatial gradient 2, 4 like that, it goes up. Next, please. So if you just do the performance analysis, I take a burst signal which has a central frequency of about 60 kilohertz. Uh, if you look at this and propagate in a rod, so mode 1 propagates very well. It's a forward moving. And if you take the mode 2, you see some two small bars which are the negative modes propagating, negative speeds. It violates causality. It violates the Einstein as well as the KK causality. Next, please. So this is about the infinite speeds. Essentially, what happens at that infinite speed if you take a Gaussian signal and plot very near the region. And at very high speeds, also violate causality as there are no sharp wavefronts. That is, the response is present at all times, which is not possible. Next, please. So essentially, what we are trying to say here is the uh, the maximum gradient present in the peridynamic model is only 2. So, and any higher modes are not causal. So we can eliminate it and we can have only second order. Consider the peridynamics equivalent to your second order equation and basically solve the equation. And this required all these examination to do that. So essentially, in conclusion, we can say that the wave motion parameters, including wave modes, group speeds, frequency response, have been examined in the various non-local theories, and the agreement or disagreement to the principle of has also been examined. And especially the more contentious part is in the integral type non-locality. In summary, most of the considered theories have shown one or the other aspects of unphysical nature. In the wave modes, gradient theory show finite number of wave modes. Integral theory shows infinite number of wave modes. Depending on the model, the discontinuities in K can exist, which is a source of instability. Group speeds, existence of very large or infinite speeds, existence of infinitely small or zero speeds, existence of negative speeds, and absence of attenuation of waves in some of the modes because of the purely imaginary nature. It is also shown that the above aspects can be mitigated to a little extent by using KK relations. And the frequency response function can be used to examine the KK relation in the multimodal sense. And there may exist even discontinuities in G depending upon the type of the models. And the wave response shows infinitely large speeds may manifest as the absence of the signal front in the response histories. A negative speeds manifest as existence of the response before the time of the load, and if it is satisfies the KK relations, then there can be a load. So essentially, next please. So essentially, what we have said here is uh, the non-local waves are very complex and takes a lot of time to understand because wave propagation itself is very complex. And in non-locality, when you bring in, it is even more complex because we don't know how to answer certain unphysical. And still, there are many areas of open research that people are trying to address. So here are some of the materials that people can use it, where we have published books as well as some very good papers. I have given the list. Next, please. And these are some of the first three are my books. Used waves in nanostructures, elastic wave propagation in structures and materials. The first is the 1,000-page book, and second is the nine. It's about a smaller version of the first book. And if you really want to understand spectral FEM, there is a book on wave propagation by James F. Doyle, who happens to be my advisor at Purdue. So thank you very much. And if you have any questions, I can answer.
Thank you very much. This was quite exhaustive study. So for questions, please raise your hands and I'll call out your name as they appear on my screen. Okay, so I don't see any raised hands, so probably I'll take the liberty to ask some few details. So to just recap a bit, so you have a non-local wave equation and then you test it again different beam theories, right?
Yeah.
Okay. Okay. So what is the final verdict? If I'm an engineer, what is in your opinion that which theory I should go with it if I have to design something?
Well, that's a very difficult question to answer because uh, the best way to use these non-local theories, especially if you really want to construct models at the atomistic level. Because for continuum theories, you don't use it.
Hmm.
So if you are using at atomistic level, and and to those models apply these causal theorems and remove those spurious or unstable modes, use the stable modes and construct your solution and validate this with experiments.
So which one have been more successful? Which theory has been more successful against experimental validation?
Yeah, then if you use local models for atomistic, it will not match. If you use non-local models, it matches to some level, provided you take all these discrepancies out. That is, those modes which are showing unrealistic speeds, those modes you are taking. So you take one by one and look at it. That is my advice.
Okay, okay. Okay, and so you had two kinds of theories which you called it the gradient based and the no integral based. So,
Yeah.
okay, if you look at this gradient based, can I go? Okay, uh, oh, sorry. So, if I may look at one of the slides,
Next, you have to go a little. Yeah. Yeah.
uh,
Yeah.
so and which one are you calling the gradient based?
The
This.
gradient based is only you will have a partial differential equation. So, for example, the first two are gradient based.
I
One
see.
is the
So
stress gradient, another is a strain gradient based theory.
So when you call about gradient-based theory, these are basically classical integer order operators.
Yeah, exactly.
Okay,
So it is
okay.
basically space and time. But the integral, where you have this kernel function for evaluating the material property, which is inside. So that becomes, uh, so that's why you need to replace the integral by summation. And that summation will lead to infinite possibilities, infinite modes. Understanding becomes more and more complex.
And I see. So,
So that's
okay.
why I brought in the lattice dynamics to explain first the non-local model, because lattice dynamics is people use in most of the atomistic simulation. And
Mhm.
so how is it, and what I, whenever I use the partial differential equation, it is a continuum problem. So I'm trying to link these two, and in the process, I get all of these problems.
I see. I see. So I recall we had like two couple of peridynamics talks, and they were using it for crack propagation. But
Yeah.
I don't think so. You have in your cases you have crack, right?
Now
So
I have used all of this. This is a preliminary study. The idea of non-local models is at the crack tip there is singularity, and the singularity is removed by non-locality.
okay,
So that is the advantage. That's why people use it for crack, because at crack tip there is singular, and
I
that
see.
singularity is removed. And there is somebody has raised a hand.
Yes, there is. Professor
Yeah.
Karima, if you have a question.
Yes, I'd like I would like to ask about the wave process when it can be described by the combination of two wave equations. For example, for some time moment, there might be the usual wave process, and then after some time, kind of damped wave process or something uh, happens. Then, if we consider the total moment, we need to deal with the two different wave equations. So I would like to just understand when time moment passes through the next process. So we need to have kind of transmitting conditions, function itself, the derivative. So I would like to understand uh,
That means,
in
yeah,
application, what does it mean?
I understand that. That means you have two different systems.
Yeah.
The wave propagates here, hits the other system, and again a new wave propagates. So basically, that is the coupling of the two different wave motion. I have taken only one motion, and you have to take this and couple it with the wave motion of the second one, and then build your solution. And
Yes.
with approach like spectral FEM, if you look at, I've given the books where you can construct a spectral FEM for, say, a strain gradient, and you can construct a spectral gradient for a different model, and then couple just like a normal, we use it for FEM and get the overall solution. But make sure that each of these model doesn't have all these unphysical things, which is part of the solution. So now two things is there. You can construct a numerical solution based on by removing some, by adding some, and creating a numerical setup for spectral analysis and waves using something like a spectral FEM, which is nothing but a finite element in frequency domain, and then build any number of structures around it.
Okay, thank you.
I don't see any further raised hands. So if you
Okay.
still have a question or a remark, you may please unmute your mic and go ahead. Okay, I believe there are no further questions. So this is a good point to close this talk. Thank you very much, Professor Gopalakrishnan, for this very exhaustive study. It was very nice having you here today.
Thank you. Thank you very much. Sorry for all the technical issues.